Hi, it's Mike Sklash. I'm senior hydrogeologist at the Dragon Corporation. Dragon's an environmental consulting firm with offices in the United States and Canada. Previously, I outlined what we're going to talk about in this series of webinars and why. And we're going to look at 10 things that could help you solve your problems of groundwater and soil contamination. I'm hosting these webinars, and this is tool number one that I'm going to talk about today, conceptual site models. Conceptual site models are important because they synthesize everything we know about a site. And I've got this picture of Mount Vesuvius up as an example, and on the right and on the left we have a conceptualization of what that might look like on the inside based on literature review and that sort of thing. And that's really what we start with when we talk about remediation. We need to understand what's in the subsurface. The next area that I'm going to talk about after the basics on the conceptual site models is a robust conceptual site model. This is our approach to getting conceptual site models that stand up better to criticism that you might get in court or you might get from the regulators and so on. You want something that is going to work because you really understand the site. And then I'm going to present two case studies where CSMs were critical to the remediation at a site. So this is kind of the outline of what's the problem with remediation. Remediation problems often occur because remediation design is based on a faulty CSM. The CSM isn't telling you what the subsurface is like as accurately as possible. Remediation systems are not designed based on what is actually in the subsurface, but they're designed based on the CSM. This site that we're looking at here is a fairly simple hydrogeology with sand above silty clay. And at this site, the CSM takes into account that the simplicity of the geology, these layers are continuous aerially, and we have a good idea of how thick they are and so on. So the CSM was fairly easy to do. This CSM is not so easy. The CSM needs to integrate everything we know about a site, including hydrogeology, the release source, what it was like, the material, the timing, the properties of the release, was it soluble or insoluble, and so on. What are the concentration distributions around the site? What are the risks, the pathways, receptors, and other factors? But this particular site, the CSM, is a little bit difficult because this is a clay site where most of the material is clay, and that doesn't allow groundwater to move very quickly. But there's also fractures that we see at the site. And if you don't understand that the site is fractured, you'll get your CSM wrong. This is another site that is another indication of a problematic CSM. So at this site, if you didn't see this picture, you might be drilling all over the place and not understand where the water is flowing. Like if we drilled over where number one is, we'd have one idea of what the transporting properties of this material are. But if we drilled over at number two, we get another indication. So we need complete information as complete as possible to understand how a site behaves. And often what I find is that even if people have got a lot of information, they don't integrate the information. They don't look at, say, the geology and look at the implications of the geology with respect to how quickly groundwater would flow, that sort of thing. Finally, another example of where a conceptual site model can go wrong. If you don't get the fundamentals right, the remediation will go on, or the cost will be too high. This site here, for example, imagine if this site was covered with soil. If you were to drill at location number 1, you would describe this site as having a very low capability of having groundwater and contaminants move through it. But if you moved 2 feet over and drilled at number 2, you would have an entirely different picture of what's going on. So we need to get all the information we can in order to get a good CSM. And what I like to do is develop what I call a robust CSM. This is a way of getting a conceptual site model that will stand up to rigorous questioning by others, by, if you're in court or if you're talking with regulators. And the way I do this is to use your typical approaches to getting information on the site and then add 2 other things. I add independent data. That's answering questions directly, but from a totally different angle, like how quickly does the groundwater move and how quickly do the chemicals move? And also complementary data. I look at other ways to constrain the answer to that question, like what's the geology like and how would that affect how quickly groundwater should move? So here's a simple example with a picture of me. How old am I? The easiest way to get an answer is to look at my birth certificate. But let's say you didn't have that. You could look at independent data, figure out when I went to high school. I went to high school, started when I was 13. You could do the math and figure out when I was born if you knew when I went to high school. Or you can look at complementary data. You can look at, say, the color of my hair, which you can see is gray. And if I took off my hat, you would see there wasn't much hair there. That gives you a bracket that allows you to get an idea of how old I am without having that birth certificate. So that's what we want to do, is get independent and complementary data to supplement our conceptual site model. So this is another way of looking at building upon a preliminary conceptual site model and building it into a robust conceptual site model. And I use my geologic career as kind of an analogy. So in a preliminary conceptual site model, this is getting information before you really go out and understand by drilling in the ground or sampling and that sort of thing. You look at what's available to read, literature, the records, air photos, interviews, and so on. So like my career, I had a lot of notes and books and so on when I was a student, but I really didn't have any practical or much practical experience, much digging, much drilling, and so on. In a revised CSM, one that's even better, you start adding information by getting information in the field, geologic framework, measuring groundwater, water levels and velocities and so on, taking samples of soil and groundwater chemistry, and looking at the contaminant transport process. In the analogy of my career, new professor, lots of book learning, some lab work, but not a lot of experience doing practical things. And then we go to the robust conceptual site model. So here we've already got a conceptual site model that's pretty good, but then we add things that can constrain the model and make it convincing to other people who may not want to be convinced. And this I call the robust conceptual site model. So it integrates everything you know, and it puts that all together. And like my geologic career, where I started off with book learning, then some advanced techniques, and now having lots of experience, I combine all that. So I'm like a robust conceptual site model. So why do we need a good conceptual site model? I showed you before some examples of the complexity of the geology, but here's an example where we dealt with a landfill that ended up having over $100 million award in a court case. And a landfill, this particular landfill was in southeastern Michigan. The area was about 160 acres. The depth of interest was about 80 feet, and that gave us 3.5 million cubic feet of material that we needed to understand. But even though we had a lot of borings, about 100, that only gave you 175 cubic feet of material that you saw, and that's less than 0.005% of the landfill volume. So you need other information to help you understand the CSM. And here we're looking at conceptual site model on the right for this landfill. There were 3 aquifers. We needed to figure out how far could metals have migrated from the landfill. And typically what we would use is figure out the groundwater velocity. We'd use Darcy's law, which we'll talk about later on in the webinar series, which gives us the velocity of the groundwater. And in order to do that, we need things like groundwater flow maps. This is the groundwater flow map for the deepest aquifer number 3. And we would use this along with permeability and so on to figure out groundwater velocity. But what are some of the ways we could constrain this? Well, on the left, we see a tritium map, and we're going to talk about tritium later on in these webinars. Not today, but later on. And tritium is an isotope of water that occurs naturally, but was also a product of atmospheric testing of nuclear weapons. And we know kind of what happens with tritium in groundwater with time. So if we can see this map, we can know the age of the groundwater. Or on the right, we see an electrical conductivity map. Electrical conductivity is a fairly easy way to see the influence of groundwater contamination from the landfills. So these two things together could help us to constrain the conceptual site model based on field information. And what are some of the other ways with complementary data? Is the CSM consistent with other information like geology? If we see soil that looks like this, we have an idea that it's not going to transmit groundwater very readily. And we'd have to see something like sand to have rapid groundwater movement. Another thing that you can look at is the CSM even conceivable? And some examples of that, you could do back calculations that would give you an idea of your groundwater, whether your groundwater velocity made sense. For example, trichloroethylene, TCE. If you see that in groundwater and you try to calculate when it was released based on the length of your plume and the velocity of the TCE, and it comes out to be in the 1800s, you know that's not possible because TCE wasn't around in big quantities at that time. You can also look at whether someone saw the spill. That constrains timing. I worked at one site where they overfilled a fuel tank, and they saw that. They documented the time and date, so you know that everything has to work back to that release date. Or was there an underground storage tank? That's easy enough to find out, and that may help you to to make your CSM more robust. So I'm going to look at 2 case studies where we used conceptual site models to help a lot in picking out remediation. This first site is a site in southeastern Michigan where they manufactured aluminum tubes from aluminum ingots. And the map on the left shows the site that we're focusing on. HAA was our client. There was a little manufacturing area to the east of that called Ace Tool. And then there was a subdivision of houses that used groundwater called Drexel Park. And then down to the southeast, there was another operation similar to HAA that did the same thing. They made aluminum tubing. So prior to our involvement in 1994, investigations indicated that there was TCE in the soil and the groundwater at HAA. We knew based on that information that groundwater flowed from HAA towards the Drexel Park subdivision. However, the reports gave an unbelievably high velocity, something that you didn't normally see in groundwater, and that was something that was a red flag. The other problem is that the Drexel Park subdivision groundwater was showing TCE in the groundwater. So our client had it. The reports indicated flow was towards the subdivision. The subdivision had it. So the consultant had proposed a $9 million remediation, which was pump and treat. So we were asked to look at this. We had a fairly short time to do it because there was there were issues related to costs for the sale. What we did basically was we mobilized a lot of drill rigs, a lot of people. We did perimeter borings and monitoring wells every 500 feet around the site, and we did additional borings at suspected hotspots. So in all, we did a lot of work, 170 soil borings, more than 100 monitoring wells, lots of samples tested for soil and groundwater. We tested for hydraulic conductivity or permeability and fraction organic carbon, which allows us to evaluate TCE transport rates. We measured groundwater elevations, and we did some groundwater transport modeling. And this is what we found. This is our model, our conceptual site model. So what we found was the site, HAA site, was underlain by a perch zone, which was permeable, had groundwater that had TCE in it. And we had the upper aquitard. Aquitard is material that doesn't allow groundwater to flow through it very readily. We had a local aquifer, which is a deeper aquifer, sandy material that allowed groundwater to flow, and a lower aquitard. So we had this sort of stratigraphy. We found groundwater in the perch zone flowed to the east towards the subdivision. We found groundwater in the local aquifer flowed to the west, away from the subdivision. And we found where the star is, we found that the perch zone pinched out on the HAA property, meaning that it didn't extend to the eastern property line. This is important. What happened in the previous consultants' reports was they didn't recognize this upper aquitard. They thought the perch zone, the local aquifer were together, and what happened was they got a groundwater flow direction from west to east with a very high hydraulic gradient or slope, which they said moved the TCE towards the subdivision. So what we found was that the impacted groundwater from HAA was in the perch zone and moved to the east, but didn't go as far as the eastern property line, and that the impacted water that was under the residential subdivision was actually flowing towards the HAA property. So we were able to get a plan approved by the regulators that helped a lot in understanding what needed to be done. The state recognized that HA was not responsible for the impact in the subdivision. The $9 million remediation system was not needed. We were able to have a local aquifer testing frequency that was not nearly as rigorous or as closely spaced in time as most monitoring programs, because our modeling showed that the groundwater was moving fairly slowly, and we based our sampling on that. We got a gradual reduction in monitoring the perch zone, and the annual monitoring costs were on the order of $10,000 per year until we decommissioned. And when we decommissioned the site a number of years later, we were able to do surgical remediation of impacted soil and groundwater as the building was demolished. So currently, we're in this situation now. The building is gone, and there's no further action. So here you can see the importance of a good conceptual site model in the remediation at HAA. Second one is a site we're currently working on in Kansas. It's called the former Salina Air Force Base site, and this was what the site looks like now. So it's former Air Force Base, now used as the Salina Airport, and the industrial facility in here was all part of the Air Force Base, and even some of this residential area was part of the Air Force Base housing. The site was a strategic air command base, and so there were lots of bombers based here. And I'm going to focus on this location here. This was an area where the planes were degreased using TCE by brushes and by power washers as they ran their missions from Salina, Kansas, over Europe and back. So I'm going to focus on, again, this is the same circle. We call this the wash pad, and this is where one of the places where they wash the planes. And what you're going to see is, oh, we're not going to see it. There we go. I'm going to show you a video that shows what they did back in the 1950s, and we're going to see lots of material before we actually see them washing the planes. But this was a very important part of the defense of North America during the Cold War. And so we can see that it looked kind of cold when they were there as well. One of the things that they did, and you're going to see it at the very end, is they washed the planes with brushes and power washers, and basically let the TCE, trichloroethylene, just roll off the pavement and into the drainage system and into the groundwater. And Salina, Kansas, their water supply is from groundwater. Here we can see brushing with TCE to clean off the oil and grease from the planes on return from mission. And in a minute, we'll see them power washing. So just went right into the ground and evaporated. So here's a slide I like showing to show how much TCE they used at Salina compared to large plumes that we know in the literature. This is from Cohen and Mercer in 1993. And, the entire plume that we see here from a chemical plant in New Jersey used 72 drums of chemical. And this one in Cape Cod, Massachusetts used 7 drums. In Salina, they used 218 to 254 drums of TCE per month. They used a massive amount of chemicals that basically part of it evaporated, but a lot went into the ground. So this is the problem that the people of Salina, Kansas faced, that we had these plumes that were moving in the direction of the city wells, these yellow dots. The U.S. government in 2007 offered the people of Salina, the entities there, a sizable amount of money to clean up all of the contamination, and they were going to use it by do this by injecting chemicals into the ground. But the site characterization was incomplete at that time. They knew some information about the northeastern part, but they knew very little about the rest of the site, and they had done no bedrock investigation. So if they had accepted the money for this type of cleanup at that time, as we'll see, there would have been some problems. So we worked on a remedial investigation at the site between 2014 and 2017. We put in almost 400 borings, 28 HPTs. That's a technique where you can get high resolution indications of where permeable zones are in borings. We did 54 bedrock borings. We drilled almost 3 miles of borings, installed 70 monitoring wells and 285 temporary wells. We took 1,800 soil, groundwater, surface water, and air samples, and we came up with a conceptual site model. And kind of our mantra is put your arms around the problem, figure out how big the problem is. And this is what we saw in terms of the map. 11 plumes where we defined the sources and the aerial extents, mostly TCE, but some PCE and carbon tetrachloride. We also put our arms around the plume vertically. We figured out the depth and we characterized the geology. So this is generally what we saw in the southwest to northeast direction. We saw mostly clayey soil in the overburden that varied between a few feet and 80 feet or so. We found sandy soil. The sandy parts were very sporadic and disconnected in the southwest, but got more connected going to the northeast. We found the bedrock, and we found the water table was fairly close to the surface, but got deeper as you went to the northeast. And we found contamination in the bedrock. And the reason this site is so complex is that it's got meandering stream geology. There are 2 streams. The main one, Smoky Hill River, is a meandering stream. What that means is it moves back and forth as it moves from south to north, and we get different types of deposits. This is a meander bend, number 1. Number 2 is the inside of a meander bend where you get permeable deposits. 3 is the outside where you get non-permeable deposits. 4 is a cutoff, and 5 is a oxbow lake, something that's been cut off, and you get low permeability material. So you get aerially, you get a lot of different materials, and vertically you do. So it's very unpredictable what's where. The complicating factor is we had another creek, Dry Creek, that also was meandering. We had groundwater flowing across this, and that made it very complex. So this is our conceptual site model for Salina, which after spending lots of money on it, this is simply what we had. In terms of groundwater flow, we had overburden in the orange, shallow in the source areas, and we progressively got more and more sand lenses that became better connected as we went down gradient in the groundwater flow direction, and eventually very connected. And we had groundwater in the bedrock, number 4. In terms of groundwater contamination, the source zones, we had high concentrations. We had fairly high concentrations in zone 2, where we are getting the sand lenses starting to become more plentiful, and it's approaching, contamination is approaching zone 3 and has already impacted the bedrock. So this is our proposed remediation. It's not a simple remediation. We've got various types of remedial approaches that are appropriate for conditions that we found. And as I said before, you have to take into account everything that's going on. So not just the geology and hydrogeology, but in some places we couldn't get access under buildings where sources were. So we had to place reactive barriers down gradient. In some places, we could inject barriers like the government wanted, but this is a very small part of the remediation. And this is comparing on the left what the government offered prior to a comprehensive remedial investigation and a good CSM to what is required to clean up the site. So it's a good indication of needing good information before you can come up with a remediation that will be appropriate. In summary, remediation problems often occur because the remediation design is based on a faulty CSM. If you get the CSM right the first time, the best remedial methods will become clear. So that's it for today. I just want to point out this is the list of topics we're going to be talking about. Our next webinar will be by Jeff Bolin, our Senior Vice President. He's going to talk about the importance of interviews and site records in going towards that conceptual site model. So I want to thank you for listening in today, and hopefully you'll listen into our future webinars. Thanks a lot. Bye-bye.